Imagine that you are playing a game with your friends on a Sunday afternoon on an open field, and the challenge is to throw a stone at the maximum distance possible on the ground. Now, assuming that the power you can deliver to the stone is constant, the only variable that you have to think about is the angle at which you should throw the stone from the ground surface. So, if you throw it at a very steep, at a very flat angle, then you can throw it at a very high speed, but it will not go much further because it will land on the surface quite soon. On the contrary, if you throw it at a very steep angle, like close to 90 degrees, then it may go very high, but it will land very close to you. So, definitely it shows that a compromise is needed in terms of the angle. And if you apply Newtonian physics and calculus, the words may not be familiar to you. If you apply these physics and math, then you can arrive at an angle of 45 degrees, which could be optimum for you to maximize the distance on ground. But in order to arrive at that angle, you need to have very simplifying assumption that the only force acting on the stone is gravity of the earth, and also that the force is uniform and has the same magnitude and direction everywhere throughout the trajectory of the stone. So if you make these assumptions, then you can actually predict the entire path of that stone, and it can be shown that it will be a parabola, and you can actually even determine the actual velocity of the stone at every instant of its trajectory. So all these predictions show the power of physics and math, but in order to come up with these numbers, you are making a lot of assumptions. So let's check the assumptions. First one is that the air resistance that the stone will experience when it throughout the motion, you are neglecting that because uh, the stone is very dense and it has a very low volume, so you can safely neglect the air resistance that will try to prevent its motion in whatever direction it is moving. The air uh, has the tendency to oppose the motion. Another assumption that you are neglecting is the rotation of the earth about its axis. So when the earth will be rotating, the ground itself will be moving, but the stone has is in the air, so there will be some motion, uh, relative motion between the stone and the ground surface due to the rotation of the earth. So that's another assumption. One more assumption is the gravitational attraction of moon, which and other planets actually, and the entire solar system and all the galaxies. They also influence a minor uh, attraction for that stone. So you are neglecting that because the stones is very close to Earth, and the gravity force from the Earth is quite significant compared to these minor gravitational attractions. Another thing is that when the stone will uh, be moving, as it goes higher up and away from the surface of the earth, the gravitational force, the magnitude itself will go change and it will reduce. So when you are farther away from the earth, the gravitational force, the way it acts, its magnitude reduces. But if you assume it to, we are assuming it to be uh, having constant magnitude to arrive at these simple calculations. And also the direction, uh, when the stone will move on the laterally along the surface, uh, we are assuming that the ground is flat, but and it is quite obvious assumption because the distance that we are going to throw is not going to be very much high. But if we have superpowers and we are able to throw it like hundreds of kilometers, then the direction of the gravitational force itself will change continuously. For example, if at the starting of its motion, the gravity might be acting in this direction, but as the stone moves and is about to reach the ground back, the direction itself might have changed. But we are assuming it to be having the same direction. Uh, Another thing is, even if we consider all these assumptions, our ability to throw the stone at a flatter angle is higher. The initial assumption that I made was that the power that I can provide to that stone is uniform, but in actuality, if you can you visualize yourself that the ability to throw the stone at a flatter angle is much higher than to throw it at a higher angle because of our biomechanics. So that is a different objection altogether. So in light of all these objections, what should be our approach to dealing with this problem? So one way could be to take all these objections into consideration and incorporate them into a theory and then into our calculations, and whatever the answer comes, then we use that angle. But when the when the angle at which we will throw itself will have a very high error, like even if whatever number I come up with, it is not physically possible to actually throw it at that exact angle. So when that problem exists in real life, then uh, why should I complicate with all these assumptions if the influence of them is very minor? So in actuality, the exact opposite approach is beneficial and useful in practicality, and it is that we should first identify the level of accuracy that we need in our calculation and in the answer, and then we safely take whatever assumptions that we need to take with the knowledge that the effect of those assumptions is going to be very minor. So for example, take the case of air resistance. So if I take stone, the stone has a very high density and very high mass compared to its volume. So the air resistance is going to be quite low in comparison to a feather. So if I was throwing a feather, I just can't neglect air resistance because the air will have significant, you can just know from experience that the air is going to have a significant impact on its motion. So and what I can do in case of a stone is that if I know that the it is a very windy day and even a stone can have air resistance, uh, then what I can do is that I can throw it at a slightly flatter angle compared to my calculations. So if I throw it at a flatter angle than the calculation, what I know is that the way air resistance acts is that if I throw it at a very steep angle, the stone is going to face a lot of air resistance during its trajectory. So the way to deal with the assumption is that whatever calculation I come up with, I can know from experience that if I incorporated that assumption, what would have been the effect. And with that knowledge, I can actually change a little bit, make minor adjustments to the calculation, but the calculation I could do from making these assumptions, and that is the way that works the best.